Now we're going to combine the rotational kinematics that we've been doing, angular velocity, angular acceleration, angular position. We're going to combine that with the causes of rotational motion for a rigid body. That's the same steps that we followed when we went to Newton's second law. And we're going to get to an equation for rigid bodies for rotational motion that's very similar to Newton's second law. I'm going to call it the rotational version of Newton's second law. And it says this: if you add up all of the moments, this is going to sound like a lot of foreign words for now. I'm going to introduce all these topics next. But if you take all the moments or torques that are applied around some axis A, so I'm going to call this MA net, the net saying that we're adding them all up, that is equal to the moment of inertia around that axis times the angular acceleration of the body. Okay, so this is the sum of all the torques, or the reason I'm calling it M is people also call that the moments. About an axis A. Okay. This is called the moment of inertia about that same axis A. And you already know what that alpha is. That's the angular acceleration. And so this equation is going to let us relate forces and masses and things like that to angular motion of a body. And for us, this A, I'm just going to box this. This is going to be an important equation for us. That A is the fixed point or the hinge or the pin, whatever you want to call it. It's a point that's stuck to the, stuck to the surroundings, stuck to the ground, and everything just rotates around this pin. We're only going to do calculations for bodies that are fixed at some point with a pin or a hinge or whatever. You can do these kind of calculations when you don't have that and you use the center of mass of the object as that point, but we're just not going to go into that. Okay, so before you can use this equation, we need to define two things. The first one is the moment of inertia. That's the I sub A in this equation. And you can think of that as like the rotational version of mass. And then the second one is the rotational version of force. This is the torque or the moment. Either one of those is perfectly fine. So I'm going to start by defining the moment of inertia. I sub A. Okay, and the moment of inertia is a positive quantity indicating how hard it is to get a body rotating, to make it start to rotate. Okay. And it has to do with how much mass the body has and how that mass is distributed compared to the axis of rotation. So if you have a lot of mass that's distributed really far from the axis of rotation, you have a big moment of inertia, and it's hard to get the body started rotating. If you have not much mass and or that mass is pulled in really tight to the axis of rotation, that's easy to get that body rotating. I have a couple of examples I want to show you from sort of Olympic sports. Okay, so first, here we go. I have these two videos of people doing double backflips, okay? In one case, the person is doing everything they can to pull their mass in close to the axis of rotation, which in this case is their center of mass. They're trying to get their arms and legs in as close as possible to their center of mass. That produces a really low moment of inertia. And because of this low moment of inertia, you can get, when your body's in this shape, you can get it rotating really fast. Okay? And so you'll see that this guy is going to do a double backflip with all of his mass pulled in as close to his center of mass as possible. And you're going to see he completes these two flips really fast. And therefore, he doesn't have to get up very high to do it. You know, he's doing it on grass. He doesn't have that much bounce. So let's see what this looks like. And you see those two flips with his arms and legs pulled in close to his body. Okay. A person could also do two flips without pulling their arms and legs in as close as possible to their body. And that makes their body harder to get rotating. And because of that, they have to get up a lot higher in the air to finish these flips. So here's a case of somebody, this is obviously in a gymnastics facility on a bouncy floor, but somebody doing these two flips with their body stretched out. So basically, they're getting their arms and legs about as far from their center of mass as they can. You can see how much slower that rotation is. Another example of this moment of inertia idea is for a figure skater. When a figure skater finishes their routine, you'll often see them do a spin where they start out spinning sort of slowly. They have their arms and legs spread out far from their body. And then they pull their arms and legs in close to their body, and the effect is to make them spin faster. What they're doing is decreasing their moment of inertia by getting all the mass in tight close to the axis. So that's a high moment of inertia. Now she pulls everything in close, low moment of inertia, and that leads to this spin rate increasing. So I'm going to think of the double flip thing. So I showed two different ways you can do a double flip. So I'm just going to kind of sketch these two shapes. One is to get your body in a position like this, okay, and do your flips. In that case, you have your mass close to the axis of rotation. And that means that the moment of inertia of the body is low. The other possibility is the person does these double flips with their body stretched out like this. Here we have the mass distributed far from the axis. And the effect is a high mass moment of inertia. We're only going to calculate mass moment of inertia for two simple shapes. So the moment of inertia formulas the first one we're going to think about is a disk. And if the axis of rotation of the disk is at the center of the disk, then the moment of inertia is 1/2 times the mass of the disk times the radius squared for the disk. So this is R, the mass is M. The other possibility we could have for a disk is where the hinge, the fixed point, the about point, is at the edge. And it could be anywhere along the edge, and you'd have the same calculation for moment of inertia. But if your fixed point is at the edge, you would calculate this as not 1/2, 3/2 times the mass times the radius squared. The other possibility, the other thing that we're going to deal with is a rectangle. This, I guess I was doing this in red. I'm going to call this the length L, and this the width W. The first possibility we're going to deal with is if the fixed point or the pin or the hinge is at the center of the rectangle. Then the formula for that is 1/12 times the mass times the quantity length squared plus width squared. The next possibility is, let's say that we're in the middle of the short side, but all the way at the extreme on the long side. So if the hinge or the pin is at either of these 2 points B, you would calculate this the same way. And the calculation would be this moment of inertia is 1/12 times the mass times the length of the short side. So 1/12 times the mass times W squared plus 1/3 times the mass times the long side. Now, C would be either one of these 2 points. And for that one, you're always taking 1/12 blah, blah, blah times the length squared of the side where you're in the middle. So IC would be, let's say, 1/12 times the mass times the length squared plus 1/3 times the mass times W squared. And then the last one of these possibilities is if you're at any of these corners, And remember, what these dots are representing is where the pin is, or the hinge, or the axis of rotation. Then you would calculate this as 1/3 times the mass times the quantity length squared plus width squared. Okay, so with these formulas for the disk and the rectangle, that's all the calculations that we'll have to do for moment of inertia. The SI units for moment of inertia are always going to be kilogram meters squared. The next thing that we have to learn to calculate is the torque, or the moment. And I'm going to denote that with a capital M. And so in order to do this calculation, let's say we have this arbitrary body, and this is the pin. This is our about point. We're going to calculate the moments about this point. And let's say that at some other point P, so I'm going to call this point where the pin is A. This is the point where the force is applied, P. And if you draw a line between A and P, so there's that line. And now if the force is perpendicular to that red line that we drew from A to P, so if those are at right angles, I'll call this the force F, and this red line between P and A has a distance, has a length D, okay? Then the moment produced by that force, or the torque produced by that force about that pin A, is equal to plus or minus the force times that distance. How do you know whether it's plus or minus? You have to think about physically which direction this body would rotate if that point A was a pin or a hinge and you applied this force F. If you get, if the rotation would be counterclockwise, it means that the moment is positive. And if the rotation would be clockwise, it means the moment is negative, the torque is negative. So let's think about this example that I've drawn. So if this point A was fixed, so that point couldn't move, all the body could do was rotate around that axis, around that point A, and you applied a force F over here at P, would this body rotate clockwise or counterclockwise? You can see that force F in this case would make it rotate clockwise. And so to calculate the moment, you'd multiply F times that distance, and then clockwise means that it's a negative value. Well, there are infinitely many forces, directions of force that we could have applied where this line is not perpendicular to the force. So what do we do? You know, what if the force is not perpendicular to the line from A to P? Okay? Well, this is the trick that you use. You can move the location of the force anywhere along its line of action. Now you're not physically actually moving where the force is. As someone doing this calculation, you can't control that. But for doing the calculation, you can move this force along a line. And so if you have this body and this is the axis A, and this is where the force is applied, okay? The line of action is the line that contains that force, and it extends in both directions. It doesn't even have to, you can treat this force like it's acting off the body even, as long as you keep it along this line. So this green line is called the line of action. So in this case, all you do is figure out where that point P would have to be along this line of action so that the force is perpendicular to the line between A and P. So notice if I moved my point P from where it is here to about here, okay? Now the force from A to P is perpendicular. And now we can do this calculation the same way we did before. This is the D, the force is F. We multiply force times D, and then we figure out clockwise or counterclockwise. In this case, it's clockwise, and you'd get a negative value. Intuitively, so when you're trying to make sense out of what a torque does, intuitively, think of using a wrench to turn a bolt. So think of turning a bolt with a wrench. So let's say that you're trying to turn this bolt. And here's the wrench. And say you're capable of applying 200 newtons of force to this wrench. Would you want to apply your 200 newtons here? Or here? Or here? In order to turn this wrench the most easily. Now notice that you're applying the same amount of force, so it's not the force that does it, but if you applied your 200 newtons of force, if you applied that force vector going straight through the bolt, okay, notice this is the line of action of that force, okay? So it's like you're applying that 200 Newton force at the center of the bolt. And no matter what force you apply, that wouldn't turn this bolt at all. Eventually, the force that you applied would just strip this bolt right off the wall, and it still would never turn. So this would not be an effective place to apply that force to turn the wrench. This one, the line of action is this. And you would get some rotation from that, but if the bolt is really stuck, maybe it still wouldn't turn. And so what you would want to do in that case is apply that 200 newtons of force way out here. And then what you get is a force of 200 newtons times this distance d that goes all the way between these 2 points. And so you get, if this distance out to the end of the wrench is twice as big as the distance to the middle, then you're going to get a rotating effect on this bolt that's twice as big when you apply that force at the end. Let me do an example of calculating a moment. So let's say we have a rectangular shaped body, and we have a force here of 100 newtons and a force here of 200 newtons. And I'll give some dimensions. Let's say that the width is 0.1 meters. And the height is 0.5 meters. And we want to calculate the net moment or the net torque. First, we're going to do it if we assume the pin is at this point A, and I'll say that A is here. And second, separately, what if the pin is at the point B? And I'll put that here. Okay, so what we're going to do is, so for part A, we're going to assume the hinge is at A. We're going to calculate the moments produced by each of these forces individually, and then we'll just add them up. That's the way that net moment works, or that net torque works. Okay, so first, what about this 100 Newton force? What kind of torque does that produce about A? Well, the line of action of that force is this, okay? You can see that that line of action goes right through the point A, and anytime that happens, your distance d is 0. So the moment produced by the 100 is a force of 100. I'll do the plus and minus here. But we have a force of 100 times a distance of 0. And so you get 0 for the 100 Newton force. Now we'll think about the 200 Newton force. So the moment produced by that 200 Newton force, the line of action of this force is this. And so the distance d, then we would want that 200 Newton force to be moved over to this point in order for our force and our line to be perpendicular. And so the distance d then is from this red dot up to A. And so this time we have 200 newtons times a distance of 0.5. A 200 Newton force to the right acting on this part of the body, if the hinge is at A, would make this body rotate counterclockwise. And so we want the positive one. And so we get positive 100. And the units here are newtons times distance, which is meters, so Newton meters. Okay, so the net torque around that point A is 0 plus 100, so 100 Newton meters. Okay, now we're going to do the same thing, but we're going to assume that this time the pin is at B. I'm going to start again with the 100. Okay, now we have to move. The line of action is the same as it was. I guess I didn't have to erase that. So where do we have to move this 100 Newton force to make the force perpendicular to that line between our hinge and where the force is applied? We'd have to move it to this point here. And so then the distance between where the force is applied and the hinge is 0.1 meters. So we have plus or minus a force of 100, a distance of 0.1, a force over at this location acting up. If the thing was free to rotate around B, would make it rotate counterclockwise. Counterclockwise is positive, and so this is positive 10 Newton meters. Now we'll go to the 200 Newton force. The line of action of that force is this. In this case, that 200 Newton force is already perpendicular to the line between the hinge and where the force is applied. And so we have the torque produced by this 200 Newton force of plus or minus a force of 200 times a distance of 0.5 that 200 Newton force would produce a counterclockwise rotation of this body around that hinge at B. And so this is positive, and we get positive 100 Newton meters. And then, like always, once you've calculated the moments produced by each individual force, then you just add them up to get the total. So the net moment about that hinge at B is 10 plus 100, so 110 Newton meters. Well, now we have everything we need to put it all together and do a calculation using the rotational Newton's second law. So let's do an example where I'm going to say there's a disk that's connected to the wall at this hinge. And let's say that the mass of this disk is 5 kilograms. And the radius of this disk is 0.2 meters. And I'm going to say that the way we're looking at this, down is toward the bottom of the page, which means gravity is going to act. One thing that you always have to do, you always have to recognize, is that gravity acts at the center of objects. It acts at the center of their mass. So we're only dealing with rectangles and circles, and so you just have to put the weight force, the gravity force, acting at the center of the shape. So I'm going to start by drawing a free body diagram. Well, let me write what we're calculating. So let's say we want to calculate the angular acceleration of this body. So start with a free body diagram. The weight force acts at the center, and that's equal to 49.0 newtons. And then this is something you're always going to want to do at the hinge or the pin. There's an unknown force acting at that hinge or pin. We don't know what that is. So I'm going to say there's a horizontal part and a vertical part. I'll just call these Rx and Ry. These are not going to produce moments ever in any problems, but you need to have them in the free body diagram in case you're going to use Newton's second law in addition to rotational Newton's second law. So there's our complete free body diagram. And now, we're trying to get towards rotational Newton's second law. So it doesn't matter what order you do these in, but I'm going to first calculate the moment of inertia of this disk. The pin is on the boundary of the disk, and so the formula says 3/2 times the mass times the radius squared. And you get a value of 0.3 kilogram meters squared for the moment of inertia. The next thing we have to do is calculate the moments of all the forces around that hinge. Well, I'll start with the weight force. There's the line of action. You can see that the line of action, you don't have to move this force anywhere along its line of action because where that force is located, it's already perpendicular to the line between the hinge and where the force is. Those are already perpendicular. So all we need is this distance d, and that's just going to be the radius of the circle. And so the moment produced by the weight is plus or minus 49 times that distance d, which is 0.2. And then we have to think, given this hinge location and this force location, which way will this body rotate? It'll rotate clockwise. And so we want the negative. And so this comes out to be negative 9.8 Newton meters. Okay, now what about the moment produced by these forces at the hinge? Well, those are always going to be the same because the line of action of these always goes right through that pin, and so these will always be 0. And so the total moment about that hinge is going to just be this negative 9.8. So I'll write it as the net torque is equal to negative 9.8. Now we have everything we need to plug this stuff into rotational version of Newton's second law. Negative 9.8 is equal to 0.3 times alpha. And you get that alpha is equal to negative 32.6 repeating radians per second squared.